I'd like to start with a shout out to our partners. So the Data Quest is supported by the Australian Space Agency and funded by the Office of the Chief Scientist and Engineer and the New South Wales Government. And we're also very glad to welcome on board as partners Australia National University and InSpace. The organising team hails from Macquarie University, myself, and UNSW Canberra Space. We're very lucky to have partners in Doug down under Geosolutions, which is an Earth observation and computing company who are generously providing a grant of computing time to support the Data Quest. And we're also partnering with Fireball, who are another Earth observation company who run an early warning system for fires over in California and are actually based in Australia as well. So they've been very generous with their time and resources. We're hope to have some great announcements about partners in negotiation as well, but that's for a different day. Okay, so we'll probably just go for an hour. Today, I'm going to provide a little introduction to Frontier Development Lab and why it's great and why we're partnering with FDL to run the Bushfires Data Quest. Introduce the Bushfires Data Quest, and I'll also hand you over to my colleague Adi Chopra, who's an FDL alumni, and he'll talk a little bit about his experience of running and of operating in a full FDL sprint that takes place over in NASA Ames. We'll talk a little bit about what the Data Quest involves and how you can get involved as either a mentor or a researcher on a team, and then we'll open up for questions. Okay, so quick introductions. This is the local organizing committee. There's myself from Macquarie University, Lee Spittler, who's sadly can't be here today, but he's on paternity leave, and Russell Boyce from UNSW Canberra Space. So we're the chairs, and you can always reach out to us if you have questions. Also on screen, you'll notice Emmeline Pat Delstrom and Eric Delstrom. They're our New Zealand contingent, and they have been fantastic in linking us up to the organizations, both academic and commercial in New Zealand. Mark Chung is an FDL alumni, and he's based in the States, so it's a little bit of an unfriendly time for him. Sood Balazs, he's also somebody from UNSW Space, and he'll be giving us a little introduction and setting the scene about detecting fuels in one of our challenge themes. And I mentioned Aditya before, so he's going to be talking about his experience as an FDL person. And we also work with James Jackson, who's our local IBM contact here too. Okay, so why are we partnering with FDL? So for those who haven't heard of FDL before, Frontier Development Labs is an effort that's been running for 4 or 5 years now and has run 6 different research sprints that connect Earth observations, AI, and commercial entities. So the best in AI, the best in Earth observations, and the best in space science, trying to bring them together into a melting pot. And over the last few years, they have built a team and a system which is superb at producing great outcomes and great research. So FDL produces great research by trying to create interdisciplinary teams and focused on different challenges. And you will send around the links to the FDL websites a little later on, and you can explore some of the outcomes of FDL for yourself. FDL runs 2 different research sprints, and they happen at NASA Ames in the States and at Oxford University in the UK. So there's a European and a US focused sprint. In the US, they're focused on more to do with space science. So looking at planetary defense, space mining, looking at space resources, so returning to the moon. Very big on space weather and heliophysics. There's a lot of heliophysics projects that have happened in the past and ongoing. And also looking at exobiology and astrobiology and planet hunting. The FDL sprints that take place in Europe are much more downward facing. So they're looking at many of the earth sensing problems like floods and fires, that we want to focus on in Australia and New Zealand. And they're supported by ESA there and have the Copernicus network of instruments to draw on. FDL is all about connecting machine learning to problems that can make a big difference by applying machine learning. And when it started in 2012, the deep learning revolution was really just getting started. And FDL was one of the first people to take, or first organizations to take advantage of that and start to apply it to themes and to domains where it wouldn't necessarily have been applied before. The key to FDL success has been teaming up experts at the top of the machine learning game with domain experts from the different fields. But like the world, FDL is also changing. So FDL in later years is bringing on more cutting edge methods, sort of at the moment looking at Bayesian and probabilistic deep learning methods, and data fusion, which especially needs inputs from the different partners. So the other key to FDL is that it forms a bridge between the private and the public worlds and brings on board very big names in the tech industry like Google and IBM and NVIDIA to partner up and devote resources to challenges that are good for humanity. The outcomes of FDL are superb. So you can see here from this slide, this is a little map of the sorts of tasks that have been attempted in the challenges of FDL, and they result in deployed AI workflows, lots of published research that tends to get into some of the best journals and at the leading conferences. So for instance, in 2019, an FDL team won the best paper for the climate change at Neuro IPS, which is kind of like the Oscars of machine learning each year. I won't go into detail on that slide. You can have a look at it in the presentations, and it's also on some of the documentations on FDL website. Just to give you an example of the sort of outcomes that FDL produces, there were two different projects that I could pull out as examples from the US and the EU sprints. The first from the US last year was a project to do lunar resource mapping. And this is an example of a data fusion project. So where the teams pulled together data in, I think, 47 different layers from 7 different satellites and multiple instruments in order to create a map of the moon to point to where there might be metals on the surface. Now, the moon itself doesn't have any metals on the surface occurring naturally, but it does have lots of impact craters. And the team used the resources of Google Cloud to create this multi-layer, multi-stack map that wouldn't have been possible in any other way, and did this all in the 8-week sprint to produce the first potential resource map of where metals may lie on the moon. In a similar vein, the team in Europe built a flood prediction algorithm, which bypassed some of the very nitty-gritty physics-based solutions that were in use previously. So if you want to predict where a flood will rise and how it will flow after a particular rain event, you often need a very detailed physics model. But you can shortcut a lot of that process and do absolutely as well using machine learning. And so they applied a deep learning approach based on Earth sensing and remote sensing data and data from USGS and the Stream network to produce a machine learning tool that would allow prediction of where and when floods would peak as a function of space and time. And this did every bit as well as the very detailed physically calibrated methods. And so these are the sort of problems that FDL and the FDL methods are very good at addressing. I'll hand over to Adi, who's going to talk a little bit about his experience of FDL and why it's excellent. Adi, are you ready to go?
Yep, go ahead. I'll just share my...
I'll stop my share.
Thank you. Hi, everyone. It's great to see some familiar names I've seen around in conferences here. I hope you can all see my screen. Excellent. Thanks for joining, everyone. I thought I'd just take a few minutes to give you a bit of an insight into what FDL feels like as a participant, and in particular as an applicant as well, if you are considering or know people you would like to recommend to apply to the program. In a couple of years ago, I had finished my PhD and a couple of short postdocs, and I was looking for the next job / challenge that would both excite me, but also give me an opportunity to work with good people. And I ended up, through Facebook and emails from different people, ended up finding about this program in the US called FDL. And it was the first year where they were offering a project related to astrobiology, which is what my PhD was in right here at ANU. What I didn't know was why they would want someone like me, because I didn't really have machine learning experience back then. And I didn't know the difference between AI and deep learning and machine learning and all these kind of terms. But thankfully, the application form was quite simple, and it remains very simple. And based on, I guess, my experiences previously in a number of different science and non-science projects, they ended up nominating an Australian to go there and work there for 8 weeks at NASA Ames with an amazing group of people. When I got there, the introduction we had on the challenge was what you see as the title right now: what can AI tell us about life in the universe? NASA wanted to use the cutting edge machine learning technology in Silicon Valley and elsewhere to apply to the search for life in the universe. And with just that as the guiding principle, they said you have 8 weeks, unlimited amount of coffee, and you'll partner with Google Cloud. So you have basically the compute resources that people would kill for. And we want you to do something good with it. Now, to help us all out in that process, I was joined by a couple of postdocs and PhD students as well. Will Fawcett was from Cambridge, who had a particle physics experience, but had machine learning expertise in that domain. Rod, I like to say, had a specialization in working for the NSA, but he couldn't tell us what he was working on. It seems like he was analyzing satellite images for the Defense Department in the US using machine learning. And Aaron was an astronomy postdoc or PhD student back then in Japan. And I had the astrobiology experience. We had mentors who were, again, from an astronomy background, most of them, or a machine learning background. In particular, Anna Maria and Massimo were the machine learning mentors. They had both experience at it, but also knew how to apply it really quickly to solve problems. And Chris and Daniel were amongst the mentors we had from the science perspective. For a bit of inspiration, working at the SETI Institute there, we also had Frank Drake in front of the Drake equation. And as you can see, we had the other Drake join us as well, very briefly. Now with that challenge, it actually took us a couple of weeks to nail down what we were going to do. We had conversations with people like Jill Tarter and Frank Drake and many others in the NASA Ames community about how we could use machine learning to solve a problem for the astrobiology community. The data quest in Australia that we're talking about today is in a very similar stage where we've got the technology, we've got ideas, and we really need to come up with challenges that are well defined so that we can put some of these data sets to use and build tools that will be useful to the community in the near future. We workshopped a whole lot of different potential projects, everything from exploring non-biological nucleotides, searching for the limits of life on Earth. There was one idea where we would use the entire Google Images archive to see if we could design an AI to distinguish life from non-life. So no idea was crazy. And we ended up, as you can see on the image here, getting rid of a lot of ideas very quickly. But eventually we distilled it down. This is a plot that shows kind of a record of all our conversations with different people. We essentially took transcripts of that and made it into a Wordle plot that you can see here. And we decided to focus on a problem that was quite timely and remains timely now, which was with the big telescopes like the James Webb coming online soon and ground-based telescopes, we need to understand the atmospheres of exoplanets. And we are quite way back in terms of development of a pipeline to be able to use telescopic observations to understand whether there's life or not on the planet. So what we realized is there was a current problem. Essentially, we knew there were lots of different types of potentially habitable planets, and they all had some sort of atmosphere, and we wanted to know what kind of surface temperature and physics and pressure range would be present on these planets. And one way to look at that is to look at the Earth's history and look at how the Earth's pressure and temperature regime on the surface has changed as the Earth's atmosphere has evolved over the last 4 billion years. So we started looking at existing models for planetary habitability, and there were quite a few different models out there. Something that was missing from a lot of them was biology, and we thought maybe, you know, that's something that we could work towards in the future. But right now, could we use a model as complex as something like this and combine it with our knowledge of the Earth's history of atmospheres over the last 4 billion years and try and predict what was happening on the surface of the planet that was Earth? And then can we extrapolate that to all the other planets out there? Here's an example that shows what Earth might look like with, or Earth's atmosphere would look like with or without life. So this is Earth today, and this is a model of what the abundances of different gases might be if you didn't have life on the planet. So a key one that's missing is obviously oxygen. This one here is missing because there's no life to produce it. What we ended up doing was actually not a machine learning project in the first instance, but a data gathering and creating an efficient workflow project, which is what the Data Quest in Australia this year is going to be a bit more about, where we took an existing model produced and used at the University of Washington at NASA Goddard. There was a Fortran 67 code, very complex, very hard for people to understand, and ran really slowly on even the best computers. And we essentially put it onto these containers called Docker environments, where you can ship them off on big whales onto the Google Cloud. And because we had access to essentially a Google data center, we were able to scale up the number of models that could be worked on in parallel. One of the unique things about the particular model we were looking at is it starts from Earth, and it has to then explore nearby models and build that up, and then you can use that as a starting point to explore further out into the multi-parameter space. Here's an example of what we did, where we started with one planet and we changed the abundances of CO2, methane, and water, things that life can control on a planet, really. And the colors show how we are sampling different temperature and pressure regimes on the surface. So this model kept going on, and eventually we ended up sampling something like 250,000 different atmospheres in a matter of days using the compute resources that we had. And we filled, we started seeing patterns about what different planets would be like under different kinds of compositional atmospheres. This plot might not look like much, but this is where machine learning comes in, is because there are lots of gaps in this plot, as you can see. But to make it more efficient, the next step is to essentially apply machine learning to really quickly populate the rest of this plot and work that out. So that's a description of the science and how we got to it. And I think the Data Quest is, to some extent, very similar to our project, where we are not yet ready to launch it as a tool that can be used by the fire service or by researchers trying to study fire behavior. but there's a lot of data out there. Like we had a lot of data over Earth's history that we could use, and we had to label it and tag it and put it together to put it to good use. And the hope is that in the future, we'll be able to come up with a nice AI based model that combines biology on Earth with atmospheric dynamics. And indeed, as a post FDL alumni, I was excited by this and ended up putting it as proposals for postdocs. And I'm happy to say that it got selected, and this is now my next postdoc. So if you want to work through, you know, what kind of problems you could work on for bushfire challenges, we had this really simple question. We then nutted it down into this template, I guess. What were we trying to solve and using what? And we ended up coming up with something like this. The exoplanet modeling community needed comprehensive and fast atmosphere models because the current models were slow and limited. And we did this by building an ML optimized search algorithm using data from the NASA and BPL faculty, and using some techniques that I've invented here. There's nothing called deep imagine or deep acceleration yet, but this is how we were defining our challenges. And this is what the Data Quest team is currently going through since the last few weeks, is refining our challenges so that we can apply it over the coming months. To give you a bigger context, for me, we weren't working in isolation. There were other teams as well who were working on slightly different parts of this astrobiology problem, where they were looking at how do you use AI to essentially do spectrum interpretations and reduce that to atmospheric composition. So how do you take data from a telescope and use machine learning to identify what kind of perhaps biosignatures might be on that planet. And we're working in tandem, which will again be the case this year with the multiple teams. They'll be working on slightly different projects, but collaborating both in their own skill sets, but also trying to make sure that we are all working towards a common goal at the end of the day. It's, as Cormac was saying, it is a community-driven effort. And, you know, there's just 4 of us here, but behind it were, before I did the project, about 3 years of FDL alumni who were always available to help us and guide us. And I think that will be the case this year as well in Australia. And we are hoping that this will be just the beginning of our FDL journey in Australia, and it will expand to many more projects in the future, perhaps things and ideas that you have already. And I'll stop there. Thank you.
Okay. Thanks very much, Adi. That was excellent. We'll have time for questions afterwards. I'd like to move on because I know some people are time constrained. Let me share my screen again. Okay, just to talk a little bit about the mechanics of how FDL works. So like most of you, I think I'm from an academic background, and it can be a slow process going through the paper writing and then the peer review and waiting for collaborators and waiting for things to happen. There's a lot of waiting and a lot of grinding that goes on to try and get new research done. So FDL works a little bit differently. It's more of an agile process, and we think it's a new mode of research. It's the bigger FDL, and what we'll be doing with the data challenge or the data quest, is based on the main FDL cycle. FDL is a 1-year cycle that's focused on an 8-week sprint that happens in the middle of the year. And some of the important milestones on this cycle are on this plot here. One of the most important, which we started the process for the data quest last week, is the think meeting, or in our case, the little think meeting. And this is where the challenges get refined and debated so that they are suitable for a research sprint type challenge. And we also want to operate in an area which is on the very edge of science and makes best use of machine learning. So we've asked ourselves the questions whether the questions that we've addressed or we plan to address are good for machine learning, are operating on the edge of what's possible, and also have the data available. The team recruitment is happening at the moment. So Emmeline and Eric will talk a little bit about the application process. That's an ongoing process for the larger FDL sprints too. But in the background, as we define the challenges, there's also a large effort to prepare the data for machine learning. And if for those of you who are machine learning experts or who've dabbled in it, you'll often find that this is 60, 70% of the process is actually making sure that your data can be ingested well into a machine learning system of some sort. And so we'll be attempting to do that over the next few months before our challenge actually starts in August, because we only have a 1 week sprint with a little bit of support on either side. And we want our teams to hit the ground really fast and running very, very fast from the very first day. The 8 week sprint happens, and it's a full-time effort. Teams in our Data Quest will be expected to take time off from their normal jobs as well and devote themselves to a full-time research on the challenges that we set. But you'll be supported by our industry partners who will supply compute support, and by our expert mentors who will know everything that there is to know about fires and ML and help direct the research as well. And in the main FDL sprints, there is the rest of the year is spent refining the solutions, engaging with the teams again at a low level, and then polishing everything up so that it's ready to deploy and be released on GitHub repositories as an open source data product, and also presented at some of the best conferences that we go to. Our sprint is going to be timed to fit in to the end of the main FDL sprints in NASA and Europe. It's going to be a one week intensive effort, but we'll have these bookend periods, these on-ramp and off-ramp periods, where we'll try and engage the teams, get them used to the compute environment, and then after the sprint is finished, take whatever outcomes come out of the individual projects and polish them up in the same way as the main FDL. Like the rest of FDL this year, because of COVID, it's going to be conducted online. So we'll be developing the tools that are necessary to do that. And we'll be supporting 4 different teams. The teams will consist of 2 experts in fires and 2 experts in machine learning and Earth observation, and we'll be pairing you up. So you have to apply as a pair. So if you've got a pair of fire specialists, or you're a pair of machine learning specialists, or a pair of Earth observation specialists, or you can find some of your opposite counterparts. That's how you have to apply. And as Adi says, we're not really expecting you to solve a problem completely in one week, but it is very possible to determine with a high degree of confidence how a challenge will work out, and get a bare bones prototype out, which can then be taken further for the rest of the year. Okay, I'll skip over that. These are the dates. The main sprint will take place from Friday 7th of August until Friday the 14th. And we'll have these periods before and after for a couple of weeks where we'll engage the teams, get them to meet their mentors, and then support them to write papers and to polish their code for a few weeks after as well. I'll just skip over this. For the supervisors in the room, if you have PhD students who are potentially thinking of applying, this is a great networking opportunity. So we have support from a wide range of academic academic institutions, and we're getting on board a number of different institutions as we speak. So CSRO are in talks with us at the moment, and we are chatting to them about using a wide range of satellite data from synthetic aperture radar. So that's a very underexplored area in fires research at the moment. One important point here as well is that we will be paying people. So the teams who come in, we're not going to just expect them to give up their research career for a week for nothing. So we'll have a stipend of $1,000 per team member for the duration of the sprint. And when we identify mentors who will be expected to give some time to support the team, we'll also be paying the mentors a similar amount. I'd like to, I know it's getting on time now, so I'd like to hand over to three of the leaders that have been debating what the challenges should look like. I should say that we had our Little Think meeting last week, and we got together our emerging community, FDL community here, to debate the challenges and make them a little bit more suitable for a data quest. We've identified three different people who are interested in leading different groups, and have started off a great discussion around these different areas. And these are the different areas that we have identified as being appropriate to run a challenge in the data sprint in August. Can I ask Sue to talk first on the topic of improved fuel assessment? Thanks, Sue.
I would like to share a slide, please.
Oh yeah, no problem.
Hi, I am Sudhanta Balage from University of New South Wales Canberra Space Group, and I took part in the improved fuel assessment discussion last week. I will talk about it in terms of data and algorithms as we are now approaching the date. So basically, we want to have some kind of a remote sensing data, some kind of an algorithm that will predict the availability of the fuel on the ground, and that will feed on remote sensing data. They can be hyperspectral optical data obtained through satellites, synthetic aperture radar, and other remote sensing techniques. And one possibility is by use of supervised algorithm, we can actually train a machine learning process with field data, the field measurements of the fuel moisture content, and high integrity, any other high integrity remote sensing data that can be correlated with the fuel and moisture content of it. Currently we are at the state of deciding which remote sensing data and selecting them, and also the suitability of the ground truth data, which is the field data that is available. And then we need to bring them into a machine learning compatible format, and that requires some processing on our behalf, such that AI algorithms can be trained. So this will be the zeroth level process where you will have some kind of a result, provided that the data actually can make such prediction. We might be able to answer questions such as which combination of remote sensing data are suitable for predicting fuel mass content on the ground, and which of the parameters are the critical parameters that actually gives the fuel mass content on the ground, and what are the effective algorithms that will actually deal with this data and become predictive tools, and any other questions that we have not conceived at this point. Exciting bit comes with the possibility of the unsupervised algorithms, where the questions that can be answered only from the data without actually ground truth. These are of the nature of anomaly detection and things like that. And then there's a class of algorithms that can be used supervised and semi-supervised mode. And these have a potential of making good discoveries, things that we have not conceived as organizers. Also, there is a risk factor involved with this, that the data may not be suitable and we may not get anywhere with it as well. We are at a state where we are deciding on which data are suitable, who can provide us the data. We need to come up with some kind of a working hypothesis. This hypothesis is just so that we will process the data in some suitable fashion. They may not necessarily be true. They may not necessarily be 100% true, and they may not be given to the researchers who are competing. The data set should be provided in such way that it is compatible with AI and machine learning other algorithms. Considering our format being short, we cannot follow the US format where a lot of raw data has been dumped on the competitor. We probably will have to do some processing, and that involves a very difficult problem to solve. If you provide a raw data and with a total of 3 weeks or so, 2-week ramp up, 1 week of sprint, I think sometimes up to 90% of the time is spent on cleaning up the data and making them suitable. So it may not be compatible with what we are doing. On the other hand, if we clean and process the data too much, it may facilitate, the first ground level naive assumptions, naive models, and quick solutions. And also the processing of the data, we make assumptions, and those assumptions will be inherited by the researchers as well. So we have to find the right formula where we will do some cleanups and keep the flexibility and the actual hypothesis that researchers will use will not be affected by it, but it can still be finished in a 1-week sprint. And we are right now looking for people who can help us with both acquisition of the data and the processing of the data, and in this discussion of exactly what we should be, how much we should be processing. Thank you very much.
Okay, thanks very much, Sud. And I should note that so we had our little think session last week, and we expect to have our challenge definitions done in another week or so, and we'll be engaging with our core researchers to get all of the process that Sud was talking about done over that time. I'd like to go to Tara Strand. Is Tara here?
Yes, I am.
Thanks, Tara, for calling in. I know it's not a great time for you, so appreciate that.
That's all right. Yep.
Do you want me to share the screen with the slide, or do you want to go for your own way?
No, if you could share the screen with the slide, that would be perfect.
No problem. Okay.
Great. Thank you. So this is about early detection, and I just want to start off with that this is really a game changer. If the earlier we detect fires, the faster appliances can respond, the faster suppression can happen, and importantly, the faster communities can be forewarned that there is a fire in their area. So it really has a big implication in the applied sense. And when we think about what we have flying in the skies as far as remote sensing, there's a lot of data that's been coming in the historically. It's been coming in for at least 10 years. And there are a lot of new sensors that have recently gone up and deployed on various platforms. And we can think about, for example, Himawari 9, which is coming online for fire in the next year and has already been tested somewhat by the Bureau of Meteorology there in Australia. But the thing is we're still not fast enough in our detection. And we believe the team got together, we had a really good discussion, and the team came up with this conclusion. What if we used machine learning algorithms to blend the existing data sets that we have streaming towards us? For example, we have MODIS, which is really good on the spatial resolution, but poor on the temporal resolution. And we have Himawari, which is great on the temporal resolution, but variable on the spatial resolution. So if we could use algorithms that blend these data sets together, can we come up with something that is a faster cadence and a higher spatial resolution? The other thing the team discussed was there are a lot of unused spectrums on these sensors that are not used for fire. And can we investigate these unused spectrums that are used for other applications to determine if they actually are indicating fire at a time when the bands that are currently in use aren't showing fire. So basically the current methods aren't optimized for the spatial temporal resolution that's really required. It's great what we have, but it's not quite enough. It's not efficient enough. On top of that, there are a lot of false alarms in those data sets, and algorithms to help us remove those false alarms on a consistent basis are needed. And so the team thought about this, and we realized that in the US and in Australia, there's a massive data set that's already tagged and labeled, and it's ready to be used to train machine learning based algorithms. And we could pull onto that data set and prep it for the 1-week sprint. And we could use that to look at these various questions and maybe answer these questions. If we blend these data sets together, or can we see something earlier? And can we use these other spectrums to sense that fire when perhaps the sensor wouldn't sense it normally with the current spectrum bandwidth that it's using? Now, I think the real long view on this is that then we could design the sensor, right? So this piece not only can change the way perhaps we detect and respond to fire, but then it could help us design the next sensor that goes up in the next 5 years, or it can help us design how we interpret the data coming out of Himawari 9, for example. So I think this is really exciting, and it has a lot of implications. Downstream, for example, it will be embedded into incident command and incident response to the fire. So it is a great little piece. Thank you.
Fantastic. Thanks very, very much, Tara. I should mention as well that we are actively engaged with the people on the ground. So we have representatives from the Rural Fire Service and institutions like AFAC Predictive Services, who actually manage a lot of the earth sensing data and build tools for the on-ground firefighters to work with. And so we want to inform ourselves of what they need, and that in turn informs what we want to get out of the challenge. Okay, brilliant. And finally, can I go to Jason, please, who's going to talk about machine learning and fire behavior models? Is Jason there?
Unmute yourself. Hi everyone, apologies I haven't found the time to actually get some slides together, so I can just talk you through a few dot points. I think there's a lot of low-hanging fruit that we could look at with respect to fire behavior modeling. I think just following on from Tara's bit about early detection, I think, you know, from my point of view, the real challenges for fire behavior modeling into the future are all sort of the extreme end of the spectrum. So the large fires, which tend to be the ones which, you know, destroy whole townships and so on. They're the ones that we really have the challenges to modeling. A lot of those fires start out in remote locations by lightning, so there's an immediate link there to being able to better you know, predict where these sorts of ignitions are going to occur. So I think there's really good scope for blending you know, remotely sensed data feeds with you know, simple terrain indices that already exist for predicting lightning ignitions and so on. So there's all these sort of opportunities, I think, with looking at sort of you know, data fusion and incorporating different models in this sort of platforms. The other thing I see you could use satellite data for in combination with other remotely sensed feeds like line scans and things like this. Multispectral line scans are used routinely by the fire services. You can use those to really try and help us establish quantitative occurrence frequencies for certain extreme fire behaviours that we know exist out there, but we don't have a good handle on how often they're occurring. Understanding that gives us a better scope for being able to understand when fires are likely, or how often fires are likely to escalate to extreme levels. And so I think there's really good scope there to be able to use machine learning and other sort of image processing algorithms to try and understand that better. And in fact, that's something we've already started to look into in connection with the New South Wales bushfire inquiry that's going on here at the moment. But I think there's good scope for widening that exercise. The other thing I see is you can use satellite data to look at sort of some of the strange patterns of burning that these extreme fires exhibit. For example, they tend to, when you get one of these extreme fires, you tend to find an absence of hotspot data, which is kind of anti-intuitive, but it's related to the fact that these things burn so intensely that they tend to burn everything. So on the second pass of the satellite, everything's sort of being burnt. So there's a possibility to use machine learning to try and better identify some of those landscapes which are prone to these extreme sort of wildfires. That leads you on then into being able to develop better models for predicting blow-up fire conditions and improving our understanding of when a particular fire is likely to develop into a pyrocumulonimbus firestorm. Okay, you need to bring in things like data on sort of weather systems and fuel availability and moisture content, particularly critically low fuel moisture content. And again, that just gives you a better scope, I think, to be able to understand which parts of your landscape are more likely to develop these sorts of events. Another big problem which has been sort of floating around in the fire literature or the fire community for a while now is this concept of fire radiative power, which is routinely measured by satellites. But the problem is that measuring the radiative power from a fire doesn't really tell you much about the convective potential of the fire, which is really the important thing when it comes to deciding whether these things are going to blow up into the large coupled fire atmosphere events with lots of embers and then blow into towns and things like that. So trying to understand how your routinely measured fire radiative power relates to the convective power of the fire, I think would be a really valuable exercise to do. Tara also mentioned one of the dot points I've got here, which is about downscaling your high temporal, low spatial resolution satellite data using your high spatial, low temporal resolution data. So taking something like Himawari and coupling it with something like Sentinel to try and develop some sort of downscaling algorithm which enables you to sort of get a better picture of the spatial detail of a fire at a more frequent or more highly resolved temporal resolution. If you can do that, then that gives you really good scope for being able to sort of do live tracking of fires, and then that feeds back into your ability to be able to then assimilate that data into fire simulation platforms, which allows you to sort of get a better idea of what the initial conditions are for your simulation, but also on top of that to sort of feed that back into a machine learning process, which can then actually try and improve the data, the models which are underpinning those simulators. Yeah, so that's what immediately came to mind when I was set to think about it.
Fantastic. Thank you very much, Jason. And thanks to Sud and Tara as well. Great summaries on all of the topics. If you can, please stick around for a little while, and we may have some questions for you after. But if you have to go, I completely understand as well. Okay, so let me go back into my share screen again. So I'd like to talk a little bit now about the application process, and can I call on Emmeline to just give a quick overview of that?
Yeah. So yeah, I know that I think probably we're itching to go to Q&A now, so I'm just gonna summarize just briefly the application process, and it's pretty straightforward. Again, the application is open right now up to the end of the month. And really the goal here is to have 4 teams, as Parmak mentioned, of teams that have 4 persons each. But the application is for teams, minimum 2, maximum 4, which would mean that we would be able to mix and match the teams that are going to be complementary kind of in terms of their background. So what we're looking for really are doctoral and postdoctoral level participants with either AI or machine learning or data science background or domain expertise in the problem area on bushfires, or you can also have a hybrid. And then also the fact that even if this is an online program, it is pretty intensive, and which is why we're really focusing on looking for participants from Australia and New Zealand, so that the time difference are all kind of like going to be the same, since it is going to be pretty intensive. In terms of the requirements, they're all on the website, but again, the major requirements here are basically a CV of each of your team members, a team reference, so preferably somebody who can vouch for all of the members and the team's experience and expertise working together. A 500-word description of your interest and participation, and then a 300-word description of evidence proving your team has worked together in the past. If you get to sort of like the down selection, expect that we would be interviewing you. And then also, I think expect that the announcement will come towards the end of June. And as Cormac said, we are going to be making sure that each of the individuals that are going to be participating will have a stipend during the actual program. I think I'll end there and then just answer questions.
Okay, fantastic. Thank you very much. We've reached the end of our presentation. So really we're just into the questions and answer phase. So I'll just stop my sharing of screen and let me know if you have questions for myself or Emmeline or the rest of the team, or perhaps some of our research leads as well.
Right, I have a question. So I'm Javan Shi. I'm one of the directors of Australia Institute for Machine Learning. So I'm a machine learning professor. I may bring in one of my postdocs or a student in, but myself would be the mentor. But as a mentor, would I be considered as one of the 4 members? Because you have a cap on how many people you can be in a team, right?
Yeah, so there's a cap on the number of participants and teams that we can support, but we're trying to identify up to 8 different mentors who would be willing to mentor the teams part-time over the week of the sprint, and also give some time on the on-ramp and off-ramp periods, and mentors will be paid as well.
So maybe what I meant by mentor is different from what you meant. So I guess the mentor information is about the mentoring all the teams, right? So I was saying, if I were to bring my some of my group into this, I would support my team, right? But will myself be considered as one of the 4, capital 4, because we have domain expert like Mark Brown here. He may also bring a postdoc or a student. So if only 4 people is a cap on the team size, then myself and Mark, both are professors, are already taken 2, then we can only bring in 2, either one student or 1 postdoc. So it's not the best utilizing our capability. So just wondering the cap on there.
So we do have a cap on the number of team members, so really, you're asking the question: if you were to apply as a team member yourself, you would like to have a bigger team around you to take on the challenge. Is that correct?
Or maybe I don't have to be a participant in a team, but somehow should what's the role should be, or the role that I should be? Because we won quite a few global competitions in mining and in other areas as well with machine learning, where data fusion is the core. Is really in mining, right? You get different channels, 19 or 30 different channels from the ground, and you want to predict what's underground without drilling, right? So it's very similar to what you're doing here. And back then we have a much larger team. So normally, if you just have 1 or 2 people to implement, then you don't get much done within 1 week. But if you have a bigger team, that's so.
So I do understand your concern, and there's going to be quite a bit of work that happens between now and August to actually prepare the data set. So we expect to have the questions to be addressed, nailed down within the next 2 weeks, and we'll immediately start getting the compute environment ready and identifying the data sets that we need, bringing them on board, and then starting the preparation in the background. So we don't anticipate that the teams will need to do too much of the data wrangling in order to ramp up. And we will be getting them involved a couple of weeks beforehand at a lower level, so that when it comes to the full-time sprint, they'll be able to run. As regards the question of sort of bringing a bit more support on board, it's something we haven't really thought about, actually. So I'll need to probably get back to you on that, or have an offline conversation.
Yeah, that's all right. Thanks.
Any other questions?
So there are questions on the chat.
Okay. Yep.
Well, I've got a question. David Bruce from Adelaide here. Look, I can completely agree with Javan. I've been in this situation before, and I think the more expertise you can add to the problem, the better the solution. So managing the domain experts is important. But my real question is about the preparation. I think there's in challenge number 2, there's at least 5 or 6 satellites that we would look at training, developing training material from, and that's a non-trivial task, and I think it should start now.
Yes. And we certainly do want to start now. Yeah. So within the next couple of weeks, we'll be starting off, and we'll need the input of the community to do this, because this is really a community effort.
So just how that's managed and on what sites and times, etc., is pretty critical, especially if it involves different sensors such as SAR. So I'm just saying that we could have that conversation soon. It would be really useful.
Yeah, fantastic. And I'd like to connect with you offline, and also put you in touch with our compute partners at Doug, who are providing all of the compute power for us as well. And we have access to their systems right now, and so we can actually start tomorrow if you are interested in giving us a hand. Okay, so some questions on the chat. When is the deadline for the application, and who can be the team members? So postdocs and late-stage PhD students are the targets. So I think we've kind of answered that already, hopefully. Will the data sets be made public after the competition? So the data sets and everything that comes out of the data quest, and this is true for FDL in general, are for the good of humanity. So they will be open source. All of FDL results are published on GitHub repositories with the algorithms and sample data sets. And we would expect to do the same here as well. The benefits for our commercial partners come from first and early and preferential access. And the open source licenses, which the outcomes are published under, don't preclude doing some commercialization work with them also, but they're, in general, it's for the good of the rest of the world. You can go to NASA firms to see the labeled data sets. Okay, so sorry, that was Tara answering the question. Okay, so are there any questions from the people who are on Zoom at the moment?
I have one, yeah. Time frame. So there's 2 months. So there's after two weeks sprint, right? There's quite a few months until December or January when you want to present the result. Does that mean every team have actually really much longer time than 2 weeks to develop this?
Well, we have a grant of computing time from Doug that covers the period of the sprint and the ramp up and the ramp down period. So we don't have a guarantee after that. However, we are in talks with other organizations to do the hosting and provide additional resources. And of course, if it's successful, I would anticipate that will be carried on as well. So I can't guarantee anything now, but there are plans afoot that will hopefully extend. So
we have GPU process, super big GPUs in-house. Yeah. We don't really need cloud compute. Our compute is better than most of the other compute you can get. But we have that, so we are not limited into this just 2 weeks compute, right? Because we'd rather spend a few more months to work on this and to deliver something that can benefit the society. So we are not really in this just for the price, but we hope that we can do something that be useful. So
that's fantastic. We would love to have you on board as partners. Let's definitely connect after this over email.
Yeah. Okay.
Yeah, I have got one question.
Yes.
Because remote sensing techniques are very good, but they have got a lot of limitation for detecting fuel load accumulation. And we often use these techniques together with some of the crucial data set, which is routinely maintained by some of the emergency services, like vegetation type, their fuel load accumulation rate, et cetera, plus some field information, which sometimes they often keep record of fuel moisture also.
Yes.
So are we going to access those data set? Because one of the things which I suspect that remote sensing technique alone won't be able to find everything, even if we are using deep learning algorithm or some other methods.
The answer is yes, if we can get access. So we're still currently defining what data sets that we actually need. So the three different challenge areas which were presented are being actively worked on. You would be more than welcome, and we'd really appreciate if you would join that conversation with the smaller teams. And if you have ideas on what data sets to access or how to tune the challenges, we would really welcome you to get involved. So please do connect.
Because our fire and emergency services, they use some of the data set on routine basis, like different vegetation types, their fuel accumulation curve, fuel moisture content. And at this moment, on a routine basis, they are not using remote sensing data, which they should be using.
Yes, absolutely. And I think one of the interesting projects that we started to discuss yesterday with CSRO was access to a large multispectral synthetic aperture radar data set that comes from multi-institutions worldwide. And that might be a good complement to measuring fuel loads as well. So
it's still because with radar data, it is more research intensive rather than application intensive. And still we have to work on whether it is effective in detecting fuel load and burnt area across all vegetation types, or it just do for selected vegetation types. European Space Agency has got very good example. They use SAR data for routine crop monitoring, and they use some of the meteorological models together with radar data, which we lack here. So these are some other aspects which has to be looked into.
Great, and I believe this has came up in the conversations between the experts that we had last week as well. So please do get in touch, and we'll use your expertise to try and refine the challenges a bit more.
Can I just jump in? Do you mind?
Yes, Tara, go ahead.
Just to say, we do have access to a lot of ground data through the various fire agencies, and they were on that call that Cormac keeps referring to, and they're quite excited about this. So I think if a data set is needed, they can help facilitate that. So absolutely, we don't want to just go with the remote sensing data sets. We want to blend what we can and what we have available in each theme. So yeah, absolutely.
Yeah, just on top of that, no, can you hear me? Yeah, I'm Xiuping. Yeah, I'm Xiuping Jia from USW Canberra. Yeah, just in terms of data, I'm thinking about a little bit technical part. Do you provide the ground truth? So eventually you can evaluate the performance using same labeled data, and also probably each team, we don't need to collect our ground truth data ourselves.
Well, it also, I guess we wouldn't necessarily limit ourselves to labeled data sets. We might end up using unsupervised methods, but essentially whatever data sets that we can glean from the fire service or the different remote sensing satellites and agencies we will use. So really, I can't answer your question yet because we haven't settled on exact definitions and exact data sets to be used. So that work is still going on.
Okay, yeah, thank you.
Okay. Okay, any other questions or comments? I would very much like to hear from people if you have ideas or if you want to get involved with the challenge definition. Send an email to the dataquest@trillium.tech email address, and we will link you into the different research groups. Last week, the meeting I keep referring to, the little think meeting, we're convening working groups on each of the 3 different challenge areas. And for the experts who want to wade in and help define something that will be that will make a useful challenge, we would very much welcome your input. If you email me, I'll add you to the Slack channels and the lists that we're going to make, and then we would hope to narrow down our final challenge definitions in the next 2 weeks or so. And this includes identifying data sets and how much computing power we would need. And we also definitely want machine learning experts to add to our faculty. And so one thing I should mention as well that probably didn't come across yet is that the Data Quest is the first attempt to run an FDL event in the local area, but it is the precursor to building a full chapter of FDL. And we expect to have a full 8-week sprint in 2021 and also expand to a number of different areas. So full FDL does remote sensing, it does space science, and we would expect to expand to other fields depending on the interest in the local area as well. So this is getting in on the ground floor on a program that's been running elsewhere and has an extremely good success rate. Okay, so I guess if there are no other questions, we'll stop there. And I'd like to thank everyone for coming along. I'm available to answer any questions over email, or if you want to have another chat over Zoom, then just reach out to me at the Data Quest email, and I'm very happy to jump on a Zoom call. And thank you very much.
Thank you.
Okay. Thanks, everybody.
Bye-bye.
Bye-bye, everybody.